This is AP Precalculus Notes for Topic 2.8, Inverse Functions. All right, an inverse function will undo a given relation. Every inverse function relation can be found by switching each x and y value. Should be doing red from here on out, but in some situations this process is intuitive, but in other times it might not be as obvious. In these cases, it is important that we understand the concept of inverse relations, as they will help us tackle a variety of problems. Let's look at this numerically with tables, graphically with pictures, and analytically with equations. First up is what I consider to be the easiest, tables, doing the numerical analysis. So to find the inverse relation of a given table, we are just going to switch the x and the y values. So let's do that. Instead of the x value being here, the x value is going to be down here, and I'm going to put the 1 down here. And instead of putting the -1 in the y, we're going to put the -1 in the x, and we're going to put a -1 up here. And we're going to do that all the way through, which means -1, 2, 0, 2 are going to be the x values, -1, 2, 0, 2 are the x values, and y values are going to be 1, 3, 4, 6, 1, 3, 4, and 6. All right, so the original table is a function. Yes, it is a function, because each input, or each x value, I should say, my handwriting here, x value has exactly one y value. However, the inverse function is not, I'm going to do that in all caps, is not a function because the x value, well, I guess, let me explain this in words and then I'll write it down. If I tell you, go to the height when we're at 1, and you'll be like, okay, I clearly know I'm going to go to a height of -1. If I say, go to 4, what's the height at 4? 4, okay, the height is clearly 0. Okay, this is a function because I know where to go. I know where the heights are. But over here, if I tell you, okay, what's the height at 2? You'll be like, okay, 2, it could be you, or it could be you. Are you asking for this height or this height, Mr. Sindel? And I'll tell you, I don't know. That's why this is not a function. I told you what's the height at 2, and you can't answer me. It's not a function. So I'll just say, because 2 y values for 1 x value. All right, so let's do a graphical analysis, aka with pictures. So we're going to sketch the inverse function of a given relationship, and it has some ideas over here. The general idea is to switch the x and the y values. You could make a table. Let's go ahead and do that really quickly. So if I make a table, let's go ahead and say this is going to be, I have some room right here. We'll pretend this function is f, shall we? If this function is f, then we'll make a table of the original x and f of x values, and then we'll make a new table of the x and f inverse of x values. Again, this f inverse function means it is an inverse of the power of -1, which seems kind of weird, but it is the notation that we use for inverses. All right, so what do we have here? This is, I'm just going to circle, these are the points that I want to list in my table, so just a series of 4 points, -2, -1, -1, 2, 2, 1, and 4, 3. Again, we know how to take the inverse of a function when I have a table. I've made it into a table. We just need to switch all of our x and y values. Therefore, these x values are now going to live over here. And I'm going to say that these are now -2, -1, 2, and 4. And all of these y values are going to live over here. And this is going to be -1, 2, 1, and 3. All that's left to do is to graph these points. So -1 to -2, -1, -2 is, I want to graph this in red though, and that's going to go to 2, -1, 2, -1. So these 2 points are going to be connected. And next I'm going to go to 1, 2. 1, 2 is this point right here. These 2 points should be connected. And finally 3, 4. 3, 4 is up here. These points should be connected. Excellent. All right, so that's the general idea behind sketching inverse functions from a graph. Good question down here in example 2b. Is the original relation a function? So this is really asking what's called the vertical line test. So vertical essentially, if I draw a vertical line and I make it so that I can move it, I have technology so I can actually do this, but you guys are going to have to do this in your mind's eye, in your imagination. If I were to move this line, does this red line here ever intersect this black line more than once, like twice, thrice, 3 times, 4 times, more than once? So we'll be looking only on this black line and see if my vertical line intersects more than once. Never does, never does, never does, never does. In fact, let me circle exactly the point that I'm doing. So never does, never does, never does, never does, never does, never does. It only intersects once at all points, therefore it is a function. So the original is yes is a function. Yes is a function. If it's asking why, it's because it passes the vertical line test. And I have a feeling that I'm going to need to write underneath this to talk about the inverse function. So let's grab you and say yes, and then I'll point to the original function. And my color coding here is off a little bit because my blue line is my inverse. So let's go ahead and change this to my blue. And let's do the same thing now with the red function that I graphed. So this function right here, let's see if it touches ever twice. So let's go ahead and grab our function. I'm going to start tracing, and oh, look right there. Look in this value. Look in this, all of this. This is bad. This is bad because if I leave the line here, this line and this line are touching once, twice, 3 times. You're not allowed to touch any more than once, which means if I tell you a value like 1.5, do you go to that height? I don't know. That height? I don't know. That height? It is unclear which height to go to, so it does not pass the vertical line test. So we'll say no, the inverse is not a function. And you can say it's because it fails the vertical line test. And this is just one of those thoughts from Mr. Sindel on going into the future. There's a way to tell, let's go ahead and go back in time for a sec. There's a way to tell, let's pretend that all of this stuff was gone, and I only had this function. I didn't make any of these graphs. All of that stuff was gone. Is there a way to tell that this function, the inverse of this function, will pass the vertical line test? Yes, it's what I call the horizontal line test instead of the vertical line test. The vertical line test made a line and was checking, does it touch any time more than once? And the answer is no. Check the horizontal line test. Horizontal line, so far so good, so far so good, so far so good. And dun, 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 this line right here fails the horizontal line test. Therefore, the inverse of this function will not pass the vertical line test. So you can do a horizontal line and be like, oh, it touches 3 times. Therefore, I know it will fail the vertical line test when I take the inverse. All right. And then there's this cool other property that I want to talk about too, which is the graphs of the inverses are reflections over the line y equals x. Again, another way of saying this is y equals 1 over 1 x plus 0, which means I go up 0 on the y-axis, and I go right 1, up 1. So if I come up here, I'm going to go start at 0, I'm going to go right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1. If I draw a line that goes through these points, check this out, through these points, this line is the line of reflection. You can see that this point was reflected. You can count the diagonal units, half a diagonal unit, half a diagonal unit. From here, it's 1.5 diagonal units, 1.5 diagonal units. This is half a diagonal unit, half a diagonal unit, half a diagonal unit, half a diagonal unit. And it's something interesting. Whenever the lines are on this line, or I guess whenever my original function, this black function, crosses this line of reflection, this point will always be one of the points, no matter what. Like, it's going to be on the normal function, and it's going to be on the inverse function as well. Any point that's on the line y equals x, you don't even reflect it. It's still the same point. Interesting, right? It'll come and help us later. All right. And then finally, we have to do the analytical, like how to find inverses just with equations. And it tells you some steps over here. I'm just going to do them for you. The general idea here is you're going to switch the x and the y value. So again, you kind of want to think of the f of x as a y value. You're saying y equals 3x minus 7, right? So think of f of x as the y value. And from here, I'm going to switch this y value with this x value. This is what the equation now looks like. It says, I want to do this with not a dashed line though, x is equal to 3, I want to say y here. You can say y, but I prefer being super accurate and saying this is f inverse of x minus 7. You might say, Mr. Sindel, you're supposed to write f of x. Why'd you write f inverse of x? Because we switched. Every single time that you switch the f of x with an x, it is now the inverse function. Now what we have to do is just set this f inverse of x, get it by itself and isolate, and then we're done. I need to get rid of minus 7, get rid of the 3. Let's get rid of the minus 7 first because I'm undoing PEMDAS, and I'm going to add 7 to both sides, add 7 to both sides. So x plus 7 is equal to 3 times this f inverse of x. X goes down a little bit lower. And finally, to get rid of that multiply by 3, we're going to divide both sides by 3. And therefore, f inverse of x is equal to this x plus 7 over 3. And there's my final answer. This is how you find an inverse algebraically. You switch the x and the y, you solve for y. So I just would like to note, like, I've been using this notation as for a while. We should talk about that right now. That inverse is written as f inverse of x. And I read that as f inverse of x. All right. So this next one is really difficult, and I'm sure the AP test is going to love doing these because they're really tricky. How do you do this same process up here where you switch the x and the y value and solve for the y value when you have multiple x values that are in a fraction? Fractions scare students, and you're taking inverses at the same time. How do you do that? I'll show you. And again, you can read these steps up here if you want. They give you a friendly reminder of the procedure. I'm just going to do it, and you can hopefully learn from that. So again, step number 1, I'm going to switch this, and this is a y value, so it's going to turn into an x. So you are now an x. And these x values over here are going to turn into y values, which means I'm going to have 2 y values. You don't have like x squared or anything. You don't have y squared. It's just any x turns into a y, any y turns into an x. So I'm going to say that this is now f inverse of x minus 2 all over f inverse of x plus 3. I have to get one f inverse of x and get it by itself, which, like, I can't just get rid of that stuff. There is a way to do it, and I'll show you that process right now. All right, so the first thing I want to do is get rid of the fraction, so I'm going to undo the division here. I'm going to multiply this side by f inverse of x plus 3. If I do that to the right side, I also do it to the left side, so let's put parentheses around that and do it to the left side as well. We're going to write f inverse of x plus 3. That is all multiplied by the left side, and what happens here is these cancel out, meaning that the right side is now just this f inverse of x plus 3. Wait, f inverse of x minus 2, sorry, that's what's left over. And on the left side, this x is going to distribute into these two terms, meaning I have an x times an f inverse of x plus a 3x. Okay, the next step is a little bit tricky, but make sure you can do this. We want to get all the f inverse of x units on one side and everything else on the other. So I'm just going to randomly say, let's put all the f inverse of x terms on the right side, which means this -2, I don't want it to be on the right side. It doesn't have any f inverse of x property. So I'm going to get rid of the 2 by adding 2 to both sides, adding 2 to both sides. I need to somehow move this f inverse of x just with addition and subtraction, which means this x is coming along for the ride. So we have to get rid of this entire term and move this entire term over here. The way that we do that is we say we subtract this x if f inverse of x. I do it to the left, I also do it to the right. I'll say minus x f inverse of x. And when I do that, what terms go away? You're gone, and you're gone, leaving behind a 3x plus 2 on the left, and an f inverse of x minus x in f inverse of x. All right, so we got all of the f inverse of x on one side. We got all of the miscellaneous stuff on the other. So this next step is going to be, I think it's the hardest step out of everything, if I had to guess. How do I convert two of these y values into one y value? And the answer is you factor it out. So here's how you factor it out. Let me move this equal sign out of the way. I'm going to say, let's factor out an f inverse of x. Factor out an f inverse of x. When I do that, I have my f inverse of x that has been factored out. What is left over is the solution to this division problem. The same thing divided by the same thing is just 1. And these f inverse of x are going to cancel out, leaving behind this minus x. And again, all this stuff is still equal to this 3x plus 2 hanging out on the left. Oops, plus 2, there we go. So we have converted from 2f inverse of x to 1f inverse of x. And finally, f inverse of x is being multiplied by stuff. So to undo multiply by stuff, I divide by stuff. So I'm going to say divide this right side by that stuff, 1 minus x. Divide that side by the same, 1 minus x. And I get my final answer, which is f inverse of x is equal to 3x plus 2 in the numerator and 1 minus x in the denominator. Again, just remember that with fractions as well, I can factor out a negative. If I factor out a negative, this is going to be negative 1x, or negative 1 plus x. It's kind of silly to say, but just be wary that answer keys that you find on the website might be a little bit off because fractions can always factor out negatives. All right, so that is the end of this problem. I should box that with ink. Say, there it is. So just to recap what we've done, the first thing we did was make it a not fraction by multiplying by that denominator on both sides. Remember to distribute your whatever your left side is. From there, we got all the f inverse of x terms on one side. We factored out by the f inverse of x and then divided by what was left over. It's going to be that same process over and over, so let's try it yet again over here in part B. Again, I'm going to start by switching my g of x values with my x values. I'm going to say that this is x is equal to 2 times that, it's not f anymore, it's g inverse of x plus 1 all over g inverse of x minus 3. Again, I want to start by getting rid of the fractions. I'm going to multiply both sides by g inverse of x minus 3, multiply that side, and multiply this side by g inverse of x plus or minus 3. So these two will cancel each other out, leaving behind a 2 times g inverse of x plus 1. The left side will distribute the x. We'll get x g inverse of x minus 3x. Let's get all the g inverse of x's on one side. So let's get, again, I'm going to choose the right side. I think it makes it look nicer, but that's just me. We'll subtract 1 to both sides. We'll also subtract an x g inverse of x on both sides. Subtract an x g inverse of x on both sides. So what's left over? Those are gone, leaving behind a negative 3x minus 1 and a 2 g inverse of x minus x g inverse of x. Now we need to factor out the greatest common factor to turn 2 g inverse of x's into 1. So I'm going to divide by g inverse of x. That's the thing I want 1 of. Divide by g inverse of x. And that means that the g inverse of x has been factored out. And what is left over is the solution to this division problem. You guys are gone, which means 2 comes over here. We're going to say there's 2. And then again, division problem, those are gone, leaving behind a minus x. And again, that's all going to be equal to negative 3x minus 1. Finally, we are multiplying g inverse of x by stuff, so divide by that same said stuff. So divide by this 2 minus x, divide by 2 minus x. We get our final answer that g inverse of x is equal to negative 3x minus 1 all over 2 minus x. For our final answer, which we will then box. It's a lot of work, but it is there. All right, let's try some more. So more in graphing inverses. We know that to find an inverse, we simply switch the x and the y values. So come down here and say the x and the y values. Graphically, this means that the function and its inverse will be reflections over that line that we already know y is equal to x. If you have trouble graphing this thing, just as a reminder, this thing is y equals 1 over 1 x plus 0. If a graph is not made up of simply line segments, sketching the inverse can be challenging. To do this, we use the fact that a function and its inverse are reflections over the line y equals x to help us sketch the inverse of the graph. So here are the steps that I'm just going to help fill out. First, you're going to sketch the line y equals x. Then you're going to mark some points that are on the original graph that are already on the line. You can also, I'm just reading ahead, select a few additional points to add on the graph based on nice points. You can either find the inverse points by switching the x and y values, which we know, or graphically you can reflect each point over the line y equals x by drawing a line that's perpendicular. And you'll see me do that. Essentially, I'm going to be counting diagonals. Like, how many diagonals do I have? It's not liking my handwriting. Perpendicular. Here, let me make it better. I don't like having the underline. Perpendicular. All right, so watch how I do these examples. The first thing I'm going to do, again, is I'm going to draw out that line y equals x. All right, any points that are on the line are going to stay on the line. So points that are going to stay on the line. You're going to stay on the line. You're going to stay on the line. Okay, next, I'm going to choose some nice points, and then I'm going to go perpendicular to the line. So your nice point, notice that it's one diagonal unit away, so I go another 1 unit diagonal, and I get my next point. We want to do my actual graphic points in blue. Find another nice point. I'm noticing that this point is nice. And then I'm going to count 1, 2 diagonals, perpendicular line. So 1, 2 diagonals means I end up right here. So I'm going to do that in blue though. Are there any other nice points that I haven't circled yet? What about this point right here? If I go diagonal and diagonal another 1, then I'm left with this point right here. And I think that's enough to graph. Just look at those blue points and go ahead and try to sketch the line through those. I can see that it's going to come out like this. And moving the iPad around, it's going to move out like that. And there is the inverse of the graph. Let's try it again. All right, in part B, it's going to be a little bit harder, but it's the same method. So let's go ahead and graph the line y equals x. And any point that's already on that line, we graph it again. So we have this point, and this point that are already on the line. And then let's find some nice points. I think this is a nice point. I'm going to count 1 unit diagonal, which means 1 unit diagonal. And what's another nice point? We've got, well, I think this point is kind of nice, right? So this point is nice, and then I'm just going to go 1 unit diagonal and a half. There's a half, and then there's the 1, which means my next point that I can draw is right, different colors on. It's right here. Are there any other nice points? Ooh, look at this one. There's a nice point. I'm going to go count 1 unit diagonal. There it is. And I think we have all the nice points because I don't see this intersecting any of these crosshair points, aka lattice points. No more lattice points, so let's go ahead and try to sketch this graph. I know that it's kind of like a whoop-de-woo, so it's going to be like a whoop-de-woo or something like that. So I think I have this general shape down. Let me try my best to actually graph that shape. So it's going to come out like this. It's going to come through here and then up and then through there. Okay, not my best work, but I think that's the general idea down. And there's arrows off to either side. Excellent. All right. So what do inverse functions actually do? If you plug a number into a function, it generally will output a new number. So for example, let's go ahead and have this function 3x minus 1. Let's plug 2 into it. Watch what happens. So 2 is plugged into this x. This is going to be, now zoom in here. Whoa, maybe too much. It's going to be 3 times 2, which is 6 minus 1. 6 minus 1, we get the output of 5. Here's the interesting thing, though. This is usually where textbooks start. If you plug that answer, if you plug this 5 into the inverse function, not to the normal function, but the inverse function, the answer should be x. because you're going backwards now. The inverse function should undo it. So going forwards, we went from 2 to 5. So go backwards, we went from 5 to 2. So we go backwards to the answer 2. It's kind of interesting, right? 2 goes to 5 in the normal function, and then 5 goes to 2 in the reverse function. So that means that inverses, they already undo a function. So let's go ahead and just generalize that. Instead of plugging in 2, let's just plug in x. If you plug in x, and we get some answer. So we plug that into a function, and then have that output. What we're going to do with this answer is we're going to plug that answer of 5, right? We're going to plug that answer back into an inverse function. We go back to the original function. So if x went to 5, 5 would go back to x. So the answer here is it goes back to x. And this is typically how most textbooks define an inverse function. Plug the function into the inverse function, and it always gets back to x. And I think that's how we're going to define it up here. This is how we define an inverse function. We're saying f and g are inverses only if you plug g into f and it's x, and f is plugged into g and it's x. You have to do it, you don't have to do it both times, but you should do it both times to show that the functions are inverses. So you must show these two things. Show that the, what we'll say, it doesn't really matter which one I put on the side. I could say that f inverse of f of x is equal to x, and also f could be on the outside. F of f inverse of x is equal to x. I guess I should say they're both equal to x. Okay, let's say it over here. We'll say that both of these things, this one and this one, both equal x. So check both. I was wrong before by saying check either one. You have to check both of them and make sure that it works. All right, so let's go ahead and check. Are these two functions inverses? I don't know. What we're going to do is we're going to plug g into f. So I'm going to rewrite the template for f. Here's f, 2x minus 3. So let me rewrite my, I'm going to make this one a red color, by the way. Let me rewrite my 2x, maybe that needs to be bigger, 2x minus 3. I have just rewritten 2x minus 3. And inside, I'm going to live g of x. This g of x is going to live inside. We're going to say that this is going to be my blue function. This is going to be my 1/2 x plus 3/2. Let's see what happens here. So the first thing that I can see is we're going to distribute the 2. When we do that, we're going to get 2 times 1/2 is just 1. So I get 1x, or just x. And then this 2 times 3 is 6. 6 divided by 2 is 3. So it's going to be plus 3. And then I have to subtract 3. And then the plus 3 and minus 3 cancel out, and this is just going to be equal to x, which means we're on the right track. This function seems to be an inverse. Let's go ahead and check the second one to verify. So I'm going to rewrite my template, I guess, for g. We're going to say that g normally is this function right here. I'm writing u down here. Here we go. This is 1/2 of x plus 3/2. And inside of my g function, I have my f function. This f function is going to live on the inside of my g function. We're going to say this is 2x minus 3. Again, we have to do some distribution. 1/2 of 2x is equal to just x, and 1/2 of -3 is -3/2. Again, that is going to be added with 3/2 plus 3/2. And you can see the minus 3/2 and plus 3/2 cancel each other out, leaving behind just an x. Because this function was just x, because this function was just x, we can now confirm that f and g are indeed both inverse functions. However, there is a problem. Sometimes you have to restrict the domain to make sure the two functions are actually inverses. So let's show you an example. Example number 7. We have a lot of examples in this homework, don't we? Or in this lesson. So I want to see if these two functions are inverses, and we have to assume that x is greater than or equal to 10. This is kind of that running question, like, why? Why does x have to be greater than or equal to 10? And there's a simple explanation, which is you have to avoid two things. Whenever you have a domain restriction, in general, in terms of any math, there's usually two things that you want to avoid. You're avoiding the bad things. Here are the things that are bad. Let me write them down. Bad things. I wonder if I'll ever add to the list, but I think there's only two. The first bad thing is if you divide by 0. And the second bad thing is if you take the square root of a negative. So for example, if I had, I don't think I need to explain it more than that. Just don't divide by 0, don't take the square root of a negative. So over here, none of these are dividing by anything, so I can't accidentally divide by 0. But this one could potentially be disastrous if the inside here is negative. So I need to make sure that the inside here is not negative, which means I want to say something along the lines of, make sure x minus 10 is always greater than or equal to 0. If that's the case, if I add 10 on both sides, then that means x has to be greater than or equal to 10. This is the domain restriction for this k of x function. In order to combine this equation and this equation, I'm combining their domains as well. The domain for this function was x is greater than or equal to 10, which means this domain also has to be restricted. So we're going to go ahead and say, okay, assume it's restricted. What happens next? Then you just do the same thing that we're doing up above. You do h of k of x and k of h of x. So let me go ahead and say that this function is going to be blue, and we'll call this function red, and we'll watch what happens. So I want to do h, this is h of k of x, k of x. And then down here, I'm going to do k of h of x. We're going to watch what happens down there. All right, so first function is my h of x function, which is x squared plus 10. Inside of that goes my square root of x minus 10. And then down here, I have k of x, which is the square root of x minus 10. Inside of the x goes an x squared plus 10. All right, so in my first problem, I can see that I'm going to square and square root, which are going to cancel each other out, meaning I have an x minus 10 plus 10, and minus 10 plus 10 turns just into an x. So far, so good. Down here, the minus plus 10 and minus 10 are both underneath the square root. You can just drop the parentheses. You don't need them when you have a leading coefficient that's a positive. Plus 10 and minus 10 cancel out to just nothing, I guess. So this is going to be the square root of x squared. And technically, this is kind of a fun problem that I don't think I've really talked about ever before. When you have the square root of a square function, this is by definition an absolute value function of x. And in order for, and this is kind of the tricky bit, I guess, in order for this inequality to be true, this only works if we have a positive number. These are true if x is greater than or equal to 0. Is it greater than or equal to 0? Yes, it's greater than or equal to 10. So luckily, I am allowed to make the statement that I can get from here to here. Nice to know. Okay, so let's try example 8. So we need to say, okay, avoid being equal to 0, avoid being equal to 4, which makes sense. Again, there's two bad things that can happen. Taking the square roots of negatives was the last one that we were worried about. Dividing by 0 is the one that we're worried about right now. This one is being divided by 0, potentially. If x is equal to 0, that's bad. That's a bad value. What value down here would make me divide by 0? Well, if I plug in 4, 4 minus 4 would be 0. That's a bad value to avoid, so avoid 4. So again, you just plug each of these functions into each other. Let's go ahead and color code this so I can make sense of what's going on. This is blue. This is red. Let's see what happens. If I have n of p of x, n of p of x, and if I have p of n of x, I need to check both of these to see what happens. Hopefully both of them will be x if I'm doing everything correctly. Let's see. So n of x is 6 all over x minus 4. And inside of that goes p of x, which is 6 over x plus 4. Then down here, this is going to be 6 all over, or it's just, 6 over x, then plus 4. Inside of the x goes a 6 over x minus 4, right? Is it x minus, x minus 4 is all in one. Hold on. Let me make sure I get this right. It's going to be 6 over x minus 4. There we go. Okay, we have both these functions set up. Let's check to make sure this works. This first question plus 4 and minus 4 cancel each other out. So I'm just going to say you guys cancel. This is going to be equal to 6 divided by 6 over x. And when you get this problem, remember, if it's a fraction divided by a fraction, it's going to be a keep it. Keep it, change it, flip it, and the 6 and 6 cross cancel, meaning we get an x here, which is excellent. That means that it probably is an inverse function. Let's check the bottom one as well. So this one is a little bit trickier, but watch what I do here. And this one is going to be equal to, it's a fraction divided by a fraction. This is going to be a keep it, change it, flip it. So I'm going to say x minus 4 over 6. Then don't forget to add 4 at the very end, so plus 4. Watch what's going to happen here. The 6 and the 6 are going to cross cancel. And then I'm just going to be left with an x minus 4. Minus 4 plus 4 also will cross cancel after that. So I'm going to say that this is equal to x minus 4 plus 4. And then from there, those two will cancel, meaning I'm just left with an x, which again is the right path, assuming that I have the domain restriction. Again, the domain restriction over here is x cannot be equal to 4. This one was x cannot be equal to 0 with the corresponding equation. All right, well, that's the first half of the notes. Then we have another 2 pages of notes, and I don't have them. There they are. Topic 2.8 notes, part 2. So I've already gone over all of this stuff. Yes, this is true. Yep, those are good. Okay, this one I think is new. X and Y values are switched. Yes, we know that. However, that means that the graphical behaviors are switched, which means the domain and the range, which domain typically refers to the X values and range refers to the Y values. The domain and range are switched because the X and the Y values are switched. Let me read this fourth one. I don't know what it's saying. A continuous function will only have an inverse function if it is strictly increasing or strictly decreasing. If a function changes from increasing to decreasing or vice versa, it will not pass the... Oh, it actually... I didn't know if this was a thing or if I had just made it up. There's a horizontal line test that I talked about at the beginning of these notes. So does it pass the horizontal line test? Yes. Then the function. Then when you take the inverse of it, it is a function. If it fails the horizontal line test and you take the inverse of it, it will not pass the vertical line test, and therefore it will not be a function. So a lot of words coming at you. Let's just jump into some examples and see if we can learn something. All right. We're assuming that f and g are inverse functions. Okay, that sounds good to me. Maybe we should make some more tables. Do I have any room for a table down here? I don't have very much room here. Where can I squeeze in some room? I'm gonna do I'm gonna make this table up here because there's some room right here. So let's go ahead and say x and I guess f inverse or g. You can say that this is f inverse of x, or you can call this, I don't know, I did double parentheses there, or you can call this thing g of x. They're the same thing. G of x and f inverse of x should be the same thing. And let's make all of our x and y values change. So I should have these values on the bottom are now on the top. I can say up here, this is going to be 6, 3, 1, negative 1, negative 3, negative 7, and then flip, so this is negative 3, negative 2, 0, 1, 4, 6. All right, so we have our inverse function, which we are also calling g of x. Let's go ahead and find the following values. All right, so first I have to find f of 0. It's the most inside of the functions. F of 0 means I'm plugging in 0, negative 1, which means f of 0 is 1. So this is really asking for f of 1. And f of 1 is negative 1, which means the answer down here is negative 1. All right, I need to do g of negative 3. And I have my inverse function up here. G of negative 3 is 4. So you can come down here and say that this is equal to 4. Now it's asking for g of 6. And again, I could have just used this table and gone backwards. 6 goes to negative 3, or I can come up here and say that 6 goes to negative 3. So we can come over here and say negative 3. G of negative 1. Okay, what is just g of negative 1? Again, I can kind of look at the table here and say I can go backwards to 1. So this is going to be 1. So now I'm just going to say what is, this is going to be equal to g of just 1. And g of 1, that 1 goes to 0. So you can come up here and say that this is equal to 0. All right, this one is using the of notation. So first I'm going to do f of -2, f of -2. So this is just a normal f function. Of -2 goes to +3. And then finally, this is going to be equal to f inverse of that 3. So if I go backwards from a 3, I'm starting down here as opposed to starting at the top. I start with 3, I go backwards to -2. To -2. And just remember that there's a fancy way of doing this. F inverse and f, they cancel each other out. Like, they should have just canceled each other out, and the answer should have just been -2, which we did get, but it's just kind of a silly way of getting there. I should have just crossed both of those out. Then finally, f inverse of -3. That means I'm starting with -3, and I'm going to go backwards, and I get to 4. All right, and then we have example 2. Function k is defined. Let k inverse represent the inverse function, and I'm looking for the minimum value of k of x. Okay, well, the minimum value of just k of x, we can see this is k. The lowest point is right here. The minimum is -3. So minimum is -3. What about the minimum value of k inverse of x? That's less clear. So let me go ahead and try my best to find that. What I'm going to do is I'm going to make a dashed line that has this slope y equals x right there, and I'm going to reflect as quickly as possible. Here we go. So I'm going to go a unit. I'm counting the diagonals, right? Half a unit goes down half a unit. This can go up 1, 2, and a half. So there's 1 and a half, and then 1 and then 2. So I have a point up here. This point goes up 1 diagonal unit, so up 1 diagonal unit. And finally, this point is going to go off the graph, but it's going to go up around here somewhere. I can actually reverse the x and y coordinates. It's just 11, 6, so I should go 6 to 11, so 6, 7, 8, 9, 10. I mean, it was up there. I think it's actually a little bit left and a little bit higher, so I can go like this. And so left and higher is going to be somewhere around there. And if I make my graph, you can see it does look like a reflection over this line. Okay, so what is the minimum value of this inverse line red function? The minimum value is -4, which actually, it makes a lot of sense. This one is -4. What I really should have been asking is the minimum values and maximum values. We're talking about y coordinates. So this one was talking about a y coordinate, but because I took an inverse function, I'm now talking about the x coordinate. This is really saying, what is the minimum x coordinate of this original black function? The minimum x coordinate was this -4. All right, and I said find k inverse of 6. There are two ways of asking this question. I could look at the inverse function that I graphed right here and say, okay, if I go to 6, it goes all the way up here to 11. But there's another way of doing it, and I think it's the faster way of doing it, is these used to be input values. They used to be x values, but because they're inverses, these are now the y values. If I have a y value of 6, what is the x value? So y value of 6, y value of 6 right here. What is the x value? The x value is, boink, I hit the function, I go down here to 11. I can say that k inverse of 6 is equal to 11. To find k inverse of 4 is saying, okay, I have a height of 4, what's the x coordinate? So a height of 4, I have an x coordinate, boink, I hit the function, I have an x coordinate of 6. All right, we're on to the last page of the notes. Example 3, function f is defined, yep, and what is the maximum value of f inverse of x? So this used to be asking what the maximum height was, but because we're talking about the inverse, is now asking about the maximum x coordinate. The maximum x coordinate now is 8. Find f inverse of 3. So this used to be an input of 3, it used to be an x coordinate, but now this is saying the height is 3. So height of 3 comes over here to 2. So we can come here and say this one is equal to 2. And f inverse of 1 means I have a height of 1. Height of 1 intersects, boom, right here down at 3. And this one is interesting. This is asking the domain of f inverse. Remember that when we have an inverse, we switch the domain with the range. So this one is really asking what is the range of the normal function. I'm going to cross this one off and say range, I don't know why there's two E's there, range of f. That's the same exact question. So I'm going to go to f and say, how much up and down am I allowed to go? I can go all the way down to -3, and I can go all the way up to 7. So between -3 and 7. So I can say between -3 and 7, including both of those, so I'll put brackets. All right, in example 4, yep, we have all of that. And I'm not even going to make a table of g inverse of x, or I guess I'm not going to graph the inverse here. I'm not going to graph the inverse here. I'm just going to use knowledge to go as fast as possible. You should be trying to do the same. So h of 6, there's no inverse. I'm just going forwards. It says the input is 6. What is the output? Output is 10. So this is going to turn into g of 10. And g of 10, again, that's not going backwards. It's just saying, hey, the input is 10. What's the height? Input is 10 here. The height is -1. So this one is -1. Boxing my final answers. All right, next we're doing h of 0. Again, no inverse. I'm just going forwards. If I plug in, this is h, this is g. Just remember. So I'm doing h of 0. There's 0. H of 0 is 3. So this is going to be, what is g inverse of 3? Okay, for the first time in these problem sets down here, I'm finally going backwards. Backwards means if I have an input here, instead of it being the x-coordinate on the x-axis, this is now a y-coordinate on the y-axis. So where's the height of 3? Height of 3 is right here, which intersects our function right here for an x-coordinate of 4. The answer here is 4. All right, next we're doing g of 8. Again, there's no inverse function, so this one is just normal. Saying, hey, go to g, go to the input 8. So if we go to the input 8 has a height of 0. I don't move up or down, so this is h inverse of 0 now. Okay, I have to be careful. This is now going backwards, which means instead of starting up at the top, I'm starting in the bottom. If I start on the bottom with 0, I go all the way back to -1. And the final question on the notes, because then there's worksheets to do after this. Final question, here we go. I'm going to talk about g, there's g, and it's inverse, so it's not talking about an x-coordinate, this is a y-coordinate now. The y-coordinate is -1. Y-coordinate is -1, which means the x-coordinate is 10. So this is now h inverse of 10. So it's saying, go to h now. H is talking about this table, and instead of starting up here, you're going to start down here because I'm going backwards. If I start backwards at 10, I go backwards to 6. All right, I know that these notes were crazy long. Thank you for staying with me. That concludes AP Precalculus Inverse Functions for notes on topic 2.8. Thank you for watching.